Welcome to Advanced Embedded Systems, Lecture 26, where we'll be talking about direct digital synthesis with linear interpolation. Remember to do your time logs. I'm going to be posting online submissions for you to submit those time logs. Lab 3 report is due by the end of today, close business. And project proposals, upload a soft copy by Monday. I'd like to take a look at them and give you some feedback. So, today we're going to talk about direct digital synthesis with linear interpolation. If you look at the website, on today's lesson, you'll see there's a XLS file, a spreadsheet. You will definitely want to take a look at this. We will be going through this example later in the slides, as well as a handout. We'll talk about how to implement a lookup table in VRAM, and I'll give you an example in that handout of how to do that. So, today, let's talk about the lookup table. How are we going to do this, and how are we going to use this on Lab 4? So, we're going to instantiate VRAM on our system in Lab 4 on the ready signal to send out values from VRAM based upon some sort of counter. That counter is going to be indexing into a lookup table, which will contain some sort of waveform, one cycle of that waveform. And that counter, typically we have the read address only reading 10 values. And we're going to use the lower 6 bits of our 16-bit value to give us fractional steps into that lookup table. And then we're going to have to linearly interpolate the values between them. So that's what we're going to talk about today. Be able to send that output as a waveform in the output. So we're basically going to build a function generator. So, how are we going to go about doing it? So, we want to set up our microblaze. If we wanted to maybe calculate the square root of a value using our microblaze. If we had a compiler which provided that function, you could just use the map library functions. On the other hand, if such a library didn't exist, how would you compute the square root of a number? You could use something like Heron's method to calculate or converge on the proper solution by essentially guessing. And using this formula, we can basically look at the next value, our next guess value, and the current guess value, or look at the current value compared to the value of s. In this formula, 1/2 of x of n plus s divided by x of n to figure out our next guess value, and eventually converge on the right value based on the number of significant figures in the value of s. And here's an example from Wikipedia on the Taylor series and Heron's method. And essentially, we start with this value of s, trying to figure out the square root of it, and we can continually guess and calculate the next guess value, plug it in, and eventually converge on the proper solution, or at least a good enough solution. But there are many ways. You can take a look at that website. There's many ways to compute a square root function. You could find some mathematical expression. Unfortunately, this usually leads to a very timely computations. You could also make a table with every possible value of x, but that's going to take up a lot of space. And then you could look that up in the table with a row corresponding to the x value and go straight into the value and pulling it up. Again, seems silly since it would use a lot of space. And we could reduce this space by, say, eliminating entries. But if we eliminate entries, then we could introduce errors to our calculations. So, if you wanted the square root for x and it wasn't in the table, you would have to basically find the closest value in the table, and then you would be compromising errors. So, depending on how you would design this table and how you're going to use it, you could use these three design constraints to figure out space, time, how long you want it to use to calculate it, how much space you have to use, and the percentage error that you want to introduce into your calculations. We're basically going to use interpolating the values between the partial values in our lookup table. This interpolation is going to be a mathematical method of creating missing data in the table. There's many methods of interpolation, but one simple method would just be generate a new value based on the average of the two values on either side of the one being created, and that's what we're going to go over today and how to do that in hardware. This is essentially linear interpolation. So if you have a value of x, which is halfway between 0 and 4, then you assume that the square root is 1/2 the distance between 0 and 4. So, shown on this graph, if we know that f of x is this y value down here, and f of x plus 4 is this z value up here, right? If we read those values from 0 to 3, taking the lower value, basically truncating down and rounding down, and the last one you jump up to the actual value of z. The intermediate values can be interpolated by drawing essentially a straight line between them. And we can estimate this function for all these three values of x plus 1, 2, and 3 by just estimating 1/4 of the way up, 1/2 the way up, 3/4 of the way up to 4, because we're breaking it into 4 sectors. So, given an example, so f of 8 down here is going to be 2, and this is actually part of the square root function. F of 8 is 2.8284, and f of 12 is 3.46. Then, right, f of 9 would be the lower value, base, plus 1/4 of the top, f of 12 minus the base. So we have your, we're going to get your delta, and that'll be your, right in the middle, 2.987 for f of 9. F of 10, you have your base value, and 2/4 of the way up. Based on that difference, we calculate f of 10 to be 3.146. And f of 11, 3/4 of the way up, we're going to get 3.305. You understand this is an approximation, and consequently we'll have error. But sometimes close is better than exact in some embedded computing, especially when time is of the essence. Here's essentially a chunk of C code that would perform that linear interpolation. We're going to call it function, where x plus I, where I is between 0 and 4 inclusively, we're given that f of x is y and f of x plus 4 is z. You're given I, and you're going to return f of x plus I, essentially that graph we're looking at. So we're looking at the delta, which is the difference shifted to the right, since we're using 0 to 4, shifted to the right by 2. And then we take that delta, multiply it by pi, so we get the fraction of that, add it to the base amount, y, and that becomes our z value. Obviously, this isn't great code, and it would be it would work a lot better if we shifted this division after the multiplication by the delta, because the difference of z minus y might be really small, and the result may be 0, and then it would cause some issues, especially if you did it in hardware. When you divide by 0, it can cause issues with your system. Essentially, here is our square root table. We have it going from 0, x values going from 0 to 16, so 0 to the square root of 4, square root of x, which is 4. You can see the actual true discrete values for the square root as we go from 0 to 4 on this chart, and it also shows the base values. So if we just use the base value and jump, then we'd have some error on that graph. So that's a lot of error between these values 1, 2, and 3. So we're going to talk about interpolation to go do those calculations to find the straight line linear interpolation between 0 and 4 on our table. So, using interpolation to find our better value of square root of 9, clearly the square root will be somewhere between 8 and 12. Obviously, we can do the 1/4 of the way. Cut, so 9 is 1/4 of the way between 9 and 12, just like we learned about. We can actually write an equation that describes that relationship. So we get our square root of 12 minus square root of 8 to get our delta times 1/4 of the way between 8 and 12. Our base, which is 8, becomes the new square root of 9. That's what we're going to do. And again, these are the 4 equations. So you have square root of 9, the delta, change in x, and change in y. So we get 1/4 of the way between 8 and 12, which is 9 and 8. And then find the delta between them, multiply it by that average, and we can get the next value for 10 and 11, those values. Normally I would divide the class into 6. Normally I divide the class up to calculate the different values for the square root of 0 to 15, but I'll show you. They're basically in the spreadsheet, the Let's spreadsheet under the 4-point square roots tab. So if you go to that spreadsheet, this is the given spreadsheet, under the Let's square root tab, you can see all the values between 0 and 15. The square root is calculated in there. This is the exact value. We're going to use a lookup table that is much condensed from this. Instead of all those 16 values, we essentially have 5. 0 and 4 other values. Right? In here, we're going to have, based on our equation that we calculated, we're going to have some base value, that's the square root of the base value in this equation, the square root of a term in the equation above. That's the base level that we're going to use to interpolate the actual value. We're going to have an offset. This is the 9 minus 8 over 12 minus 8 term in the equation above, basically factoring the distance between those two terms to essentially figure out how much the offset we are going to put into that interval. Our delta is going to be the value, the two values, the difference between them. And that's the range we're going to be covering between the two values we're interpolating our data. So we're going to have base plus offset times delta. That's going to be our square root function. And then we're going to calculate some error by using absolute value of the difference between linear interpolation and the true value of the square root function. So again, from the spreadsheet, these are on the left column the square root values, and I have calculated the base values based on that for input left table. Right, so we go from 0 to 1, 0 to 4 to 12 to 8 to 12 to 16, and calculate those square root values. So we have the base value, so 0, for 4 it's 2, 2.8, and 3.464. Right, that's what we have in that value. And I calculate the offset, obviously from 0 to 4, got a quarter of the way, half the way, 3/4, and then we're at the next value, the next base value. And the delta is the 2 minus 0 to get that offset. This one is 2.82 minus 2, so those two different bases. Subtract that value to get the delta for each of those values. 3.46 minus 2.82, we get 0.63, and the last one, we get 0.53. So then we have the base value plus offset times delta. So we're going to multiply these two columns and add it to this column to get these final values. And the percent error, we calculate that. And this is what it's going to look like when we graph those values. So we do the linear interpolation. This shows the linear interpolation that we've calculated in here. Base plus offset plus delta. And then graph that against the real square root values, the actuals. And we get a lot more error in the beginning. You can see that in the graph. And then it kind of bows a little bit until it gets to those base values where it's equal to 0. There's no error on those. So less and less error the further we move away from the 0. So I can create a function called square root in pseudo C code. It takes in a floating integer and then approximates a square root for it based upon our lookup table. The output's an approximate square root. This function does linear interpolation to calculate the square root value of the function. So, type in our function is going to be a placeholder right now, so we're just going to take a look at how the pseudocode works. So we have this lookup table. These are the values that we have in our actual 4-bit lookup, plus 0. So 0, 2, 2.82, and 3.46. So we have these values in our lookup table. And now we'll talk about what we're actually going to use for those values in a little bit. So So we index into that, we have our base address. Our index is going to be divided by 4. Is our x value, whatever we're trying to get, divided by 4. Since we're looking at 4 points on our graph. And then we're going to index into the lookup table to get our base value. So that's the lower address, starting for our interpolation. So we have our offset is our offset. We're going to AND x with this 3 value. Essentially, we're looking at the lower 2 bits of our number. So if it's 9, that's going to be a 1. And we're going to shift that right by 2. Now we're going to take the lookup table, x plus 1, and subtract that from x. So we're taking the next value in the table and subtracting that from the current base address, or x between the 2. And then we're going to return the base plus offset times delta. So essentially interpolating our function. So let's do this with an actual example. So if I use 9, and we calculated before, 9 is between index 2 and 3. Right? So I have 9. I shift that to the right. We're going to get index 2 to find that value. So I take that lookup table, I find the base value, which is right here, 2.82. Take x, and it with 3. We're going to get a 0, a 1. That's going to be our offset. We're looking at that, but then this could be a problem because we're shifting to the right and we're basically getting rid of that fractional portion that we're ANDing as we shift it to the right. And we find the delta between this value and this value, x plus 1, which is index 3 and index 2, and then return our square root. So since this is probably a problem, we're essentially getting rid of our value that we're going to find the offset. We can change our function, and now we get putting a 5th entry into our lookup table, so we can actually see that the approximation of the next value. Now we're just ANDing, instead of shifting it to the right for the offset, we're ANDing with 3 to find out our which index value we're going to get into that offset value. So for 9, it's going to be 1 out of that delta, and then later we're going to shift it after we do the calculations, right? And by the way, these fractions that were put into this int 8, I fixed your function to be essentially a fixed 8-bit fixed point decimal value at the 6th bit. So we're essentially implementing this table as a 2q2.6 binary value. Notice 1, 0, so that's 2, and then no fractional portions, and this is the hex value for it, shown in the lookup table. And then we have 2, and then the fractional portion for 828. So we're setting this up, all these values. And the last one is we're going to use, it should be 256, but we're going to get close enough with 8 bits with 255 instead for the value of 4. So 3 and as many of the fractional bits as we can have, so FF. Close enough. Then we can actually take that table and extend it to an 8-point lookup table instead of a 4-point lookup table, and then we can extend the bits to be using a 10.6 binary number instead of a 2.6 binary number. This will be more in line with what we're going to be learning about when we actually do our example of linear interpolation. So for this one, go from 0, x equals 0, and then 16 to 32, 48, 64, 80, 96, 112, and 128, and we're calculating all the actual square roots. And then we're multiplying that square root by 2 to the power of 6, because those are the fractional bits. And then we truncate it down to the nearest decimal value, because we wouldn't be able to represent anything higher than that. So we're basically shifting that binary digit over to calculate these out. So square root of 16 is 4. So multiply by 2 to the power of 6, we get 256, and then in a 16-bit binary number in 10.6 format, we have 1, 0, 0, and then a bunch more zeros in the fractional bit. So this is actually 4 in 10.61. And then this one, 5.6, 5.656. So we have 5 in the whole portion and the fractional portion, just by truncating it down to 362 and converting that to decimal. Remember, the binary point or the radix doesn't really exist, only exists to the program. So here is the graph for linear interpolation of square root versus the LUT. Base values for with the square root and the LUT function, and then here is a graph of the error over time. Notice each of the lookup table values, they come closer and closer to the actual value as the values of x get bigger. So what we're going to do is go through a sinusoidal lookup table. This is going to be like what we're going to be using on Lab 4, so I definitely pay attention to this and make sure you understand how we calculate each of these values. So in this one, this example, we're going it's on the handout. So LUT practice, I gave you these tables, and I actually gave you a graph that it'll start plotting the values for you. And it's already plotted the first two, so you don't even have to do it by hand. Otherwise, you can go to the handout that I gave you. There's also a table which you can start filling in values. We're starting out with a Q4.4 format, and each phase increment, we're incrementing by 1.1011. So we're going to plot the base, and the base plus offset times delta. So I'm going to show you a little trick. You look at a calculator, go to the same. Programmer, 11011, right? If you ignore the binary point, you multiply this value by 2 to the power of 4, you're going to get, oops, there should be binary 1, 1011. If you convert this to binary, you're going to get 27, right? So 27 divided by 2 to the power of 4. So if we shift that decimal, this number is actually 1, or phase indexing by 1.6875. So just a little over 1.5. Each index. I'm going to go through how to do this. through our lookup table. So, I'm going to actually open up this and go through it with you. So notice when you look in my table, I do not have the binary point in there. It's queued 4.4, so you have 4 digits of whole and 4 digits of fraction portion. But I simplify it and just say 27, so I'm essentially multiplying by that power of 2 to the 4 to eliminate the binary point. So I can just convert it to decimal, so I have decimal to binary, and it converts to value. You can actually copy this, and then select the others, and paste as a formula, and a lot of them you're actually going to get this next index value times, so it's going to be, you're basically adding 11011 again and again. It's like if you did it on a calculator. So if I add 27 in decimal plus 27, we get 11011, right? So it just shifted to the left a little bit. 110110. And keep doing it. And get 81. That's the third value. And so on and so forth until we get to 216, 243, and then this one, we're busting, basically overflowing our system. So we have 270 for this value right here, 10. 10 times 227 is 270. So for that one, I'm just going to do a quick minus 256 to get the truncated version. Copy that into the last of them to calculate the last values. If you do this in hardware, it's going to automatically do the rollover and just eliminate that most significant bit in that 9th position, which won't be there. Alright, so now we have all of our index values as they go through. So we're going to look at 1.687 for the first one. The next one we're going to look for 3 and some change. Right? And we're going to index into this lookup table. So we have index 0 through 15, and the value. This is a sinusoidal waveform. But we're going to index, not normally. You could index by 1 and it would just print those values on the screen, but we're indexing at a different value to change our frequency on our output. Decimal index, essentially converting it to decimal and then dividing by 2 to the 4. You can paste those in there and it'll do your calculations. The formula. Notice this is MQ 4.4 is 3.375. 5. So we're indexed to 5 and a little bit of change. 6.75, 8.43, and so on and so forth. And then it's going to roll over and go back to the beginning of the table and start printing it again because we're increasing our phase index, so we're going to be increasing our step, thus increasing our frequency. This next column, I'm basically going through and I'm truncating this number here, the decimal index, to eliminate the fractional values. So I'm going in there, so we're going to get our base index. So this is going to be index 3 for our base. So starting at the top, we have index 0 is base value 127. Index 1 is 175. Index 3 is going to be 244. This one, index 5 is 244. Index 6, 216. fill in the rest of them. Let's see, index 8, 27, index 10, 47, index 11, and notice I'm already plotting this graph at the bottom. Index 11 here, index 13, index 15. This is where we're starting to go back up. Index 0, and 7, index 2, 216, index 4, 253, index 5, and last but not least, index 7 to complete that graph. And it shows the waveforms coming out. It's a little off because we're skipping through at a varying rate through our lookup table. So we need to interpolate this to make this waveform look a little better. So these values, it's just going to look at the next value and the previous. And I'm going to go ahead and put those values in for you. So for 127, this one was B2. The next one is B3. And this one minus that one. To save time, I'm going to just be in these values. I would suggest that you go through and make sure you understand how you get these values. So it's just index 3, and I'm going to look at the next one, 4, and subtract the bottom one, and you're going to get negative values on some of these, and you're going to get positive values on some of them, depending on which one's higher and which one's lower. So then we will convert that binary or that decimal value into the binary value. And essentially I just used decimal to binary for that, whatever the bit is, for this bit, and then I'm going to make that 8 bits wide. So converting that to binary. This, paste it into all those, convert those to binary for the delta. Notice the negative values have a few extra bits of 1 just to show you that it is in fact a negative number. But then we get our offset. Our offset is essentially going to be that truncated index minus what's left. For the first one, we're going to get 0. For the next one, we have 1 minus 1.6875 minus 1. So we're going to get that offset value. And we can essentially copy that formula down to get those values. We're going to get that offset, just a fractional portion on each of those values here. And then we can convert that into binary. For this one, I actually do a little funky math, right? So I'm doing conversion to get it as a 4-bit binary offset. And I want to actually Quickly, it's just converting the fractional portion into the binary values. So I'm going to copy those in. 0.375 is 0.11, and we're essentially multiplying by 2 to the 4 power to convert it to essentially a whole number, printing those 4 bits. And then delta times offset is just multiplying offset times delta to get the value. And formula, and we're just doing delta times offset, and each of those values, and I'll show the negative values in here. And then I can actually do a binary to decimal, so I'm going to convert this to its binary equivalent using this function. Basically moving it, the binary point by 2 to the 4, giving myself 8 digits. Get the formula. 42 is a little off. Well, you can get that with 8 bits. So that one I have to do a little differently to get the conversion of the math. Concatenating the 10 bits essentially. So we got 42. That's a little bigger than the 8 bits wide. Last one, phase times that delta, or phase plus delta times offset. So this one we have base 175 plus 128, 203. And we can do that up and down. That formula. C base plus delta times offset on each of these values. And we put our final values in here. And if we did it in decimal, ultimately you're going to have 27 plus 0 for the first one. For the second one, 175 plus 208, so this one we have 244 plus 3.375. Ultimately, you're getting a truncated value, so I want to get a truncated value for all these. Basically, rounding it down, I can actually do equation for that in Excel to do it for us. So we're essentially taking our value here, adding those values, and then truncating it down to 0 decimal digits. Right? And so do that, I get 247. And truncate them all down in these values. And as soon as I start plugging into the final value number, I'm not showing you all these values. So it's going to be adding 244, 3.375, 247, 247. And as I type these in, I'm going to start plugging into my linear interpolation graph. So this one I have 244 days plus delta times offset of minus 175 to give me 242, 85, and so on and so forth. And you can go through all those. And notice you have the base, which was a little off because we're rounding down, basically truncating down to the index values. But the interpolated graph is actually looking more like a sine wave. That base plus offset times delta. We get a nice waveform for that. So, ultimately, you're indexing into the array by 27, 2 to the power of 4, 6. That's too dreadful. 7 to power 4, 1.6875. So we're indexing our phase index 1.8675 into that array, adding that index each time to basically index into 1.6875 and 1.3 or 3.375 and 5 and change, and indexing into this lookup table to create a waveform at a different frequency, and interpolating the values between so that it looks nice like the blue waveform versus the jagged-edged red waveform, which is just using the base address in that lookup table. And that concludes the briefing for today. Actually, one other thing you want to make sure to take a look at. Take a look at the handout that I gave you. So I gave you this handout. Make sure you look at the other page where I'm actually talking about VRAM SVP. Same VRAM as we had before, except I'm changing for Lab 4, we're going to change the width to be 16 bits versus 18 bits, because we're just going to add these values in. It's a lot more square because you can use 8 nipples for each of the bits, or 2 bytes in the VRAM. You'll have to understand how we initialize these values. So it's going to go from initializer value from 0, 0. Before we didn't initialize it. We initialized our VRAM to 0. And now we're going to actually initialize it to a certain value. And in the next classes, we're going to talk about how we generate a table like this. If you look at it, it reads from the right to the left. So you have memory address 0 on the right. And I'll show you. This memory address 0 is this 8000. So you have 4 nibbles, 2 bytes, 16 bits per memory address 0. Memory address 1 would be the next 4-bit nibbles to the left of that. And it counts up 0 to 15, and in the next row we're going to have address 16. And so on and so forth, all the way down to 3F. rows to get all 1,024 values in our array. And this is how I will initialize the system for Lab4. We're going to have a data output, and then we're going to read an address, and we're going to set clock. But ultimately, we're not going to write anything, so we're essentially going to hook it up like we showed you in the slides. So you're going to initialize your VRAM with this sinusoidal waveform, and Lab4, you're actually going to utilize other waveforms other than the typical sinusoid. So we'll show you how to do that, and then we're going to create some other waveforms like heartbeat or nonlinear waveforms. That would be the requirement. So it can't be a triangle waveform because that'd be a linear waveform. We're going to talk about that. And then ultimately, on every ready signal, we just output it. And that's based upon a 10.6 index value that we're going to index into that array to change our output waveform. So, see you next time when we talk about that